All right, let's continue with our next section, 4.4, logarithmic functions. Now, I think this is a concept where, and you might not have seen before, and I think this is a big, large divide between maybe the course you've taken before, like intermediate algebra, to a more higher level course like college algebra. So our objectives for this time are converting between exponential and logarithmic forms, and this is key, so make sure you finish this section knowing how to make that change. Performing calculations involving logarithmic equations, and draw a graph of a logarithmic function. Logarithmic functions. We start this section with a quick summary of two topics from earlier in this chapter. One, in our discussion of inverse functions, we learned that a function one-to-one functions with graphs that pass the horizontal line test have inverses. Two, the graph of every exponential function is a curve with no changes in direction that settles down towards the horizontal asymptote on one side and takes off from the horizontal asymptote on the other side, a curve that passes the horizontal line test. Together with these two statements, guarantee that every exponential function has an inverse, and that's a log function. So example 1, and we saw this example in the last section, 4.3, of graphing this exponential function to the x power. And we learned that as long as we have a horizontal asymptote and 2 points, we can have an idea of how our function is supposed to look like. We know that it's going to get close to our asymptote but never cross, and our other side is just going to take off towards the opposite direction. All right, so let's find the inverse. 1, we showed that it's 1-to-1. 2, we switch our x's and we change our function, change it notation to y. And then third step, we switch our x's and y's. And fourth step, we solve for y. So how do we solve for y if it's in the exponent's place? How do we isolate it? In this text, we have solved all sorts of equations with a single variable, but until now, the variable being solved for has never been in the exponent. We are stuck. How do we proceed? Since we know that every exponential function has an inverse, we will define a class of functions that will be the inverses of exponential functions. Definition. If x and b are positive real numbers, including that b does not equal 1, the logarithmic function with base b is y equals log base b of x is equivalent to b raised to the y power equals x. So my suggestion is label these values, see where each one goes. What was the y for our log? Answer is our exponent for our exponential function. Our base for the log is also the base for our exponential equation. And our answer in the exponent is our argument for the log. So make a post out of this. Have it handy. This will not go away, especially next week. Make a post-it, have it by your laptop, by your planner, wherever your study area is, next to your bed, just so you have it handy when you start studying in your room. Whatever it may be, this is key to being successful in Chapter 4. Consider where we were stuck trying to solve x equals 2 to the y power for y. X equals 2 to the y power is the same as 2 to the y power equals x. Now, by the definition above, 2 where the exponent of y equals x is equivalent to y equals log base 2 of x. We now have isolated y so that we found the inverse, which is f inverse of x equals log base 2 of x, which is the inverse of our exponential function to the x power. In general, logarithmic and exponential functions are inverses of each other. The goal of the next selection of examples is largely to make sure that equivalency definition above is committed to memory. So this formula, we're going to practice this so we can hopefully memorize it before our video is over. So let's do some examples. Use definition above to convert the following form to exponential form. When we're going from one to the other, the way I think of this is your base is the same. So your base to the exponent is also going to be your base in your log form. So here we have a base of 3. We're going to have log base 3. And then I think of our exponent and our answer switching place. And that's how I work, or that's how I think of it to remember logs. So the statement 3 to the 4th power equals 81 is the same thing as log base 3, 81 equals 4. 2 raised to the negative 4 power equals 16 will be, well, remember, we keep the same base, log base 2, and then we switch our answer with our argument. Log base 2 of 1 over 16 equals negative 4. Next, we have 9 to the 1/2 power equals 3. We have the same base of 9, so I have log base 9 of 3 equals 1/2. Lastly, 5 to the 0 power equals 1. Let's write it as a log. Log base 5 of 1 equals 0. Example 3. Use the definition above to convert the following logarithmic form to exponential form. And the same idea follows. So we have a log with a base of 4. So I have an exponent with a base of 4. And our two arguments switch. So now I have 4 to the 2nd power equals 16. Next, I have a base of 2. And then I switch to 32 and the 5. So we have 2 to the 5th power equals 32. Lastly, log base 9 of 27 equals 3 over 2. So we have 9 with the exponent of 3 over 2 gives us, I think there was a mistake here. So let's see. I think this should be 27, right? Because 9 to the 3/2 power means the square root of 9 cubed. The square root of 9 is 3, and 3 cubed is 27. Yeah, so this first argument was correct. And the second one should be, as an answer, should be base 9 with a 3 over 2 exponent equals 27. When working with logarithms, the base can be written explicitly as done with every example so far. However, the two cases where the base is simply understood. Common logarithm means a logarithm with a base of 10 is often written as a log. So notice there is no base written. When a base is not written, we assume it's base 10. So even though it's not written, there should be a little 10 there. Secondly, we also have the natural log. Natural logarithm is a logarithm of x with a base of e. Remember e from our last section? Recall how pi is about 3.14? Now e is a button in your calculator, just like pi, it's about 2.7. So with the base of e, we write ln of x. That's the same thing as saying log base e of x. Example 4. Use a definition of logarithm functions to convert the following from logarithmic form to exponential form. All right, so I want to change this to exponential form, and even though it's not written, we assume a base of 10. So in exponential form, this would be a base 10 with an exponent of 3 equals 1,000. ln, we know it has a base of e, so this would be e to the 0 power equals 1. ln, again, I assume a base of e, so it's e to negative 1 power equals 1 over e. Calculations involving logarithms. Consider the equation 3 to the x power equals 3 to the 4th power. Do you have any guess as to what the value of x must be? What is x? All right, since the bases are same on both sides, it is understandable and correct to assume that the exponents of x and 4 must be equal. So meaning, ignore the 3's, we're left with x equals 4. Using this idea and the definition that y equals log base b of x is equivalent to b to the y power equals x, we can evaluate certain logarithms. Example 5, evaluate the logarithmic expression. All right, so here I want to find out what this is equal to, right? But we're not sure, especially working with this new concept of log. So why don't I set it equal to x and solve for x that way? Our next step is to write it in exponential form. If we write it in exponential form, this would be written as 4 to the x power x is 64. What should x be? What exponent would give us 64 as an answer? That would be 4 to the third power. So we see that x equals 3. So our answer to log base 4 equals 64, log base 4 of 64 would equal 3. Log base 8 of 4. What is our answer? If we write in exponential form, this would be 8 to the x power equals 4. So this means that, well, this one might be different and harder to think about. So our next idea would be to write them in the same base. So we write as the same base. So I know that 2 to the third power gives me 8, and 2 to the second power gives me 4. All right, but our law of exponents, we know these two values should multiply, so we're left with 2 with the exponent of 3x equals 2 with the exponent of 2. All right, we drop our bases, and we're left with 3x equals 2. All right, so lastly, to solve for x, let's divide it by 3, and we're left with x equals 2/3. So lastly, our answer is log base 8 of 4 is 2/3. Now consider evaluation of the expression log base 7 of 23. As before, the evaluation can be interpreted as finding x for log base 7 of 23 equals x. Using the definition, we can write the equivalent function as 7 to the x power equals 23. But we see that, unlike the previous examples, neither 7 or 23 can be easily rewritten to make the bases the same on both sides. In order to evaluate many logarithms, we will need the help of a calculator. Most calculators contain the following two logarithm buttons. So something like this or this. As mentioned before, these two buttons will calculate the logarithm of base 10 and base e respectively. So this is log base 10, that's log base e. So what about logarithms of bases other than 10 or e, such as log base 7 of 23? Some calculators have a third logarithm button, usually written in the form of just log. As expected, this button will allow the calculations of logarithms of any base. But many calculators do not have this button. If you have a calculator that doesn't have this third logarithm button, you must recognize the following change of base formula. So there's a change of base formula which says if I have log of a base number, then I can evaluate it as log base x divided by ln of x divided by ln of b, or log of x divided by log of b. So you're essentially rewriting your entire log, and this will produce the answer you're looking for. To calculate log base 7 of 23, we can use the formula as ln of 23 divided by ln of 7, which equals 1.61. And notice you can use ln and log interchangeably however you like. Example 6. Work with a calculator to verify the calculations run into 2 decimal places. So this is for you to try. Make sure you know how to use your calculator, how to evaluate for these values using the change of base formula above. Graphs of logarithmic functions. Recall the method we used to graph exponential functions. Find the horizontal asymptote at the x-axis unless there's a shift up or down, and plot 2 points. The result was a curve with no changes in direction that settles down towards the horizontal asymptote on one side and takes away from the horizontal asymptote on the other side. Let's consider the specific exponential function, f of x equals 2 to the x power, which we've seen before. We see that we have a graph at the horizontal axis, the horizontal x-axis, a graph that passes through 2 points, and our domain is from negative infinity and our range is from 0 to infinity. So this is our characteristics of our original function. What do you see will be that of our inverse? Recall that g of x equals log base 2 of x is the inverse function of f of x equals 2 to the x power. As inverses of graphs of f of x and g of x will be a reflection across the line y equals x, and they will have opposite characteristics described below. So before we had a horizontal asymptote, now we'll have a vertical asymptote at x equals 0, which is the y-axis. Our 2 points will swap. So instead of having 0, 1, we'll have 1, 0. Instead of having 1, 2, we'll have 2, 1. Our domain and range will switch. So what used to be our domain is now the range, the range. And what used to be our range is now what our domain is. The graph of g of x equals log base 2 of x will be as follows: a curve with no changes in direction that goes downward as it approaches a vertical asymptote at the y-axis and gently increases to go to the right. So here we see we have our vertical asymptote, and we can use the 2 points similarly. We have one point that gets closer to the asymptote but never crosses, and we have another point that pulls away. Every logarithmic graph will be a single curve with no changes in direction that will approach a vertical asymptote from one direction and gently increase or decrease in the other direction. Let's consider the following functions. Starting with f of x equals log base b of x that has a vertical asymptote at x equals 0, the y-axis, and considering that g of x equals a log base b of x minus h plus k. So just as before, a k would be a shift of the vertical asymptote at the y-axis up or down, leaving the vertical asymptote at the y-axis, while a would stretch or compress the possibility and possibly reflect the y-axis across the x-axis, leaving vertical asymptote at the y-axis. The only value in g of x that can change the vertical asymptote is h. So before it was k, now it's the opposite, it's h. Altering the domain and shifting the vertical asymptote to the left or right. All right, let's go ahead and do example 7 to determine the domain and the vertical asymptote of each of the following functions. All right, so we see that nothing is being added or subtracted to x in parentheses. So we know that the vertical asymptote stays at the y-axis. The y-axis at x equals 0, and therefore our domain stays the same, 0 to infinity. Here we see we have a plus 1. So remember, it has the opposite direction, so this shifts everything to the left 1. So now I have a vertical asymptote at x equals negative 1, and therefore our domain is negative 1 to infinity. ln, which is still a log, I have a minus 2, so it shifts it to the right 2. All right, so we have a vertical asymptote at x equals 2, positive 2, and therefore our domain is 2 to infinity. In general, logarithmic expressions are defined for only positive values. So, solving an inequality can be an alternate way to find the domain of every logarithmic function. Example 7 again. Determine the domain and vertical asymptote of each of the following logarithmic functions. The domain is x is greater than 0, which is written as 0 to infinity, and our vertical asymptote is x equals 0. Here we have a domain of, so we need to solve our parentheses. So x plus 1 needs to be greater than 0. Subtract 1, subtract 1. I have x is greater than negative 1. And so therefore, our domain is from negative 1 to infinity. If you're ever unsure, you can always draw on a number line. So x is greater than negative 1. So it's negative 1 to positive infinity. Somehow a number line always makes it more easier for me to comprehend. And I have a vertical asymptote at negative x equals negative 1. All right, let's solve our argument. X minus 2 is greater than 0, plus 2, plus 2. X is greater than 2. Let me draw my number line so I can interpret this better. X is greater than 2, so it's from 2 to infinity, positive 2. All right, so the domain is x minus 2 is greater than 0, which can be solved as x is greater than 2, written as 2 to infinity, and the vertical asymptote is x equals 2. Example 8, determine the domain and vertical asymptote of r of x. All right, so let's go ahead and solve for x. 1 minus x is greater than 0. We can add x. So we get that 1 is greater than x. We want x first, and x has the smaller opening. So x has a smaller opening. X is less than 1, which we have here. So we draw a number line, 1, and it's smaller than. So our domain is negative infinity to 1. And the vertical asymptote is x equals 1. Now that we can find the domain and the location of the vertical asymptote of any logarithmic function, we can graph the curve by finding 2 points to determine which side of the graph will approach the vertical asymptote and whether the other side will be gently increasing or decreasing. Graphing logarithmic functions will require 2 steps. Just like before, determine your asymptote, in this case your vertical asymptote, x equals what? And find 2 points. Remember, one pulls away from the asymptote and one will approach the asymptote but never cross it. So let's take a look at example 9. Graph the following log function. So we see there's nothing being added to the x in parentheses. So we have a vertical asymptote at x equals 0. Our domain will be from 0 to infinity and a vertical asymptote at the y-axis. Now let's find 2 points. We can choose any 2 points on the domain, but choosing powers of 5 can allow for easier calculations. So you see how I have a base of 5? So if we rewrite it, let's make this a y. Y equals log base 5 of x. If I rewrite it to exponential form, this would be 5 to the y power equals x. So if I'm thinking as to what should I make x, you want to make sure it's a number that can come from an exponent with a base 5. So you want numbers like 1, a number to the 0 power is 1. Numbers like 5, because 5 to the first power will give us 5. 5 squared will give us 25, so you want an x of 25. And let's go ahead and see what we do. So let x equal 1. If we let x equal 1, log of base 5 of 1 is equal to 0, so we get an answer of 0. So I have 1 comma 0, which will make sense, right? Because if this is our x, this has to be our y. If this is your x, this has to be your y. If this is your x, this has to be your y. So by setting your x or by setting some examples, you can already pair up your x's and y's. All right, if we let x be 5, which we have here, what should y be? It should be 1, which we already have done. So f of 5, we get log base 5 of 5, we get 1. So I have a point 5 comma 1. Remember, it's always x comma y, which gives us these 2 points. Remember, one always pulls towards the asymptote but never crosses, and the other pulls away. So our graph looks like this. It's still some type of L-shaped figure. Using these 2 points, we know the graph must go downward as it approaches the vertical asymptote, gently increasing to the right. All right, let's go ahead and do example B. G of x equals -3 log base 2 of x plus 1 plus 4. So what's our domain? Remember, we set this greater to 0. X plus 1 is greater to 0. Minus 1 minus 1. X has to be greater than -1. So what's our domain? Let's graph this. -1 and x has to be greater. So it's -1 to infinity, which we have here as a domain. Our vertical asymptote is x equals -1. Let's find 2 points. All right, so if we let x be 1, we plug in a 1 for x, and we're left with log base 2 of 2, which is 1. So I have -3 times 1 plus 4 equals 1. Now let's do 3. 3 plus 1 gives us 4, and log base 2 of 4 gives us 2. So 3 times 2 gives us 4. So we have a log base 2, right? So the reason we chose these numbers is just work with your log base 2. I know if I write this in exponential form, this would be 2 to the y power equals x. So we have to carefully think what we want. We want numbers that have a base of 2 and will make a true statement. So I know if I want to answer of 1, my y has to be 0. If I want to answer of 2, my y has to be 1. All right, so I have an argument of x plus 1. We want x plus 1 to equal 1, and I want x plus 1 to equal 2. X has to be, I think I should have made my y. So 0 and 1. All right, let's do this again. So we subtract 1, we get x equals -1. No, I was on the right track the first time. And x equals 0. So we're trying to think of what numbers will give me here a 2 and a 4, because 2 squared gives us 4. So we see that if we add 1, we get that 2 we wanted for our x. And if we add 1 to 3, we get that 4 we wanted. So we have the points. So we have the points 1, comma 1 and 3, comma negative 2. So we see 1 gets closer to the asymptote and 1 pulls away. So there we have the graph below. Let's do another. We have ln of x minus 2. To find our domain, let's go ahead and set x minus 2 greater to 0. We have x is greater than 2. So our domain is greater than 2, so 2 to infinity. Our domain is 2 to infinity, and our vertical asymptote, since we have a minus 2, I know I move to the right 2. My asymptote is x equals 2. Now let's find 2 points. Let's do this again. So again, we want to set up our values for the base. So I know this is a base of e. Ln of a number is the same thing as log base e of a number. So I want to think. I know e to the 0 power is 1. I know e to the first power is e. So I want to stick with these types of answers. So what would make it happen so that I get a 0 or a 1? So for the first one, 3 minus 2 will give us that 1, so that our answer is 0. Or if you don't want to play with it too much, you can always use your calculator. You don't have to do this by hand. So here we have 4 minus 2, and ln of 2. That's not something I can easily come up with, right? We use our calculator, get 0.69. So I have the points 3, comma 0 and 4, comma 0.69. Let's plot them. We have them here. Remember, we have one going towards the asymptote and the other goes away. So our graph looks like this. D, r of x equals 2 log base 3 of 1 minus x minus 4. All right, so let's find what our domain is. We have 1 minus x is greater than 0 plus x. We get 1 is greater than x. Let's rewrite it with x first. X, and x has the point pointing towards it. X is less than 1. So if we graph it in a number line, x is less than, so it's shading towards the right. So our domain is negative infinity to 1, which we have here. All right, and our vertical asymptote is x equals 1. Find 2 points. All right, so let's pick our 2 points. We have a base of 3. And again, you can just use your calculator. You don't have to think so hard when you're finding your points. Since I have a base of 3, I know 3 to the first power or 0 power is 1. 3 to the first power is 3. 3 squared is 9. And 3 cubed is 27. Just to list a few. It would be nice if I had something where I'm left with 1 in my parentheses, or where I'm left with a 3 in the parentheses, or a 9 in the parentheses, something from the answer, from our exponent form. All right, if we let x be 0, we get 1 minus 0. We again return 1. So I have 2 times log base 3 of 1 minus 4. Log base 3 of 1 is 0. So I have 2 times 0 minus 4 is equal to 4. So I have the point 0, comma negative 4. If I pick negative 2, it makes this 3. So I'm left with log base 3 of 3, which is 1. So I have 2 times 1 minus 4 gives me negative 2. So I have negative 2, comma negative 2. Remember, one gets closer to your asymptote and the other one pulls away. So our graph looks like this. All right, this is all for this section, and I think we'll we'll stop here. If you have any questions, feel free to email me or post your questions.